In this video, we're going to talk about power functions and function operations. But before we do that, we're going to review a little bit of important information concerning domain and range. To start, domain, we have to remember what in the world that is. Hopefully, you recall that domain had to do with the set of all input values you can use for a function. So this is the set of all inputs, which we usually have x values, right? X values for a function. That is your domain. Now, we usually don't talk about it very much because domain's not usually very exciting to talk about because you can usually plug anything you would like into a function. However, in some of the things that we're going to be looking at in this section, we have to be careful because we will not be allowed to plug in certain numbers to the function because there are just going to be no outputs for those inputs. So there are two key issues to look out for. And if you don't see these issues, you don't have any restrictions on the domain, meaning you can use anything you want to plug in for x. The two issues are even roots and x values in the denominator. Let's talk about even roots for a moment. Guys, just to review, if I had the square root of a -4, you know that that would be 2i, right? That would be an imaginary number. So if my function, let's say, f of x, was equal to the square root of x, I would not be able to plug in negative numbers. Because if I did, I might end up with this situation here where I get an imaginary output. So we would have to say for our domain, we'd only want to plug in non-negative numbers. So it would be non-negative numbers. Another way of saying non-negative would be x values that are bigger than or equal to 0. So the smallest values we would be able to plug in would be 0, and then anything larger that would prevent any negatives to go in there. The key thing for even roots, the radicand, right, that's what you're taking the root of. The radicand cannot be negative. That's kind of the moral of the story. Let me show you a couple of examples. The first example is f of x is the sixth root of x. Well, to be honest, that's very similar to the square root of x. The key is that 6 indicates an even root. And if it's an even root, I can't take an even root of a negative number. So I would not want to plug in a negative here for x. So there's two ways of writing the domain. The way I would accept it is all x values that are bigger than or equal to 0, or you can say all non-negatives. That would be acceptable. Take a look at the next example, x plus 1 to the 13 over 8. Now this is a little bit trickier because it's not very obvious that you're looking at an even root. But remember, when you have a rational exponent, the denominator indicates the root that you're taking, and this is an even number. This is an even root. That means my radicand, remember, that's what you're taking the root of, in this particular problem is x plus 1. Our radicand, guys, cannot be negative. So to guarantee that x plus 1 is not negative, I'm going to set it bigger than or equal to 0. And if I subtract 1 from both sides of that, I'll get that x values have to be bigger than or equal to -1. If I guarantee this for my domain, I won't be taking eighth root of any negative numbers. I mean, if you want to think about it, based on this domain, isn't the smallest value of x I can plug in -1? And if you were to plug in -1, this would become -1 plus 1 to the 13 over 8. That's 0 to the 13 over 8. And you could still do that and get a 0. But if it were anything less than -1, that radicand here would be negative, and I would not be able to take the eighth root. So the domain would be all x values greater than or equal to -1. Let's take a look at if we have x values in the denominator. That's the other issue, guys. If you have a fraction with x values in the bottom, we have a problem because the denominator can never equal 0. You cannot divide by 0. So if I have this guy, f of x is 2x squared over 3x minus 1, the problem is I do not want the denominator to equal 0. So if I had to figure out what value would make that 0, I can set up the equation 3x minus 1 equals 0 and solve. I would add 1 to both sides to get 3x equals 1. Then I can divide by 3 and I'd get x is 1/3. If I were to plug in this value, 1/3, in for x, the numerator, I don't really care what that would turn out to be, but the denominator, that would end up equaling 0. And I cannot divide by 0, it's undefined. So out of all of the numbers in the world that I can possibly choose to plug in for x, the one I not want to plug in is 1/3. So for the domain, the way I would let you write it is just all real numbers, or just all numbers x that are not equal to 1/3, and I'm fine with that. So all numbers that are not equal to 1/3 are fine. But if I plugged in 1/3, the denominator is 0, and it is undefined. Let's take a look at another one. In this example, I also have an x value in the denominator. Actually, I have this expression x squared minus 1. I would hate for that to be 0 because then it would be undefined. So if I had to solve this, I would add 1 to both sides, and I'd get x squared equals 1. And if you square root, remember, anytime you take an even root of an equation, you have to do plus or minus. So now I can't use either 1 or -1, because if I were to plug it in, 1 squared would be 1, and 1 minus 1 is 0. Or if I squared -1, I'd get 1 minus 1, I'd still get 0 in the bottom. And that would be undefined. So here I would say my domain is all but x cannot be equal to plus or minus 1. Okay, let's take a look at a few more examples. What I want to do is state the domain of f of x. The thing that I'm looking for in order to state the domain are there any domain issues? So for domain issues, guys, what we're kind of really thinking of, all we're really looking for are the two domain issues. Do we have even roots? Are there even roots? Or do we have x in the denominator? If we don't have that, so what I'm going to say is, if not, then your domain is all real numbers, or just all reals, you can say. So let's take a look at A. I look at f of x is 2x plus 3, and I notice there is no even roots, and there are no x values in the denominator. As a matter of fact, f of x equals 2x plus 3 is just linear. I can plug in any x value I want. So this is all reals. I have no domain issue. Take a look at B. Now when I look at B, I have a root, but the index is 5, which is odd. There is no domain issue for an odd root, so once again, my domain is not restricted. I can use all reals, and it's not going to be a problem. Take a look at C. Here, my function has a rational exponent, and look at the denominator. It's an even number. It's 4. Guys, that's an even root. Now I have an issue. I have to be careful. My radicand, or the base of that exponent, is just x, and I have to guarantee that that is non-negative. So I'm going to make it bigger than or equal to 0. And this is my domain. So I would say here, all x values bigger than or equal to 0. Take a look at D. For part D, I have x plus 1 to the 8/5. Once again, the root here is 5. That's an odd root. And I don't have an issue with odd roots, so there are no restrictions on the domain. It can be all reals. Look at E. Here, I have a rational exponent and the denominator is 2, which is even. I have an even root. So I have to be careful. I have to make sure that my radicand, which is x minus 1, is non-negative. So I'm going to make it bigger than or equal to 0 to guarantee that. So I need to solve this by adding 1 to both sides, giving me x is greater than or equal to 1 for my domain. So here I would say all x values greater than or equal to 1 for that case. One more, look at f. F at first sight doesn't look like a problem because it doesn't have an even root or x values in the denominator, but you know something about negative exponents. If you were to make this one positive, you would write it as 1 over x squared, and now all of a sudden I have some x values in the denominator. And I have to make sure that x squared never equals 0 because I cannot divide by 0. If you square root, you would get x is plus or minus 0, which is just 0. Basically, the only number that I should not plug into this function would be 0, because if I did, I'd get 1 over 0, which is undefined. Put it in your calculator, it'll give you an error. So here my domain would be all but don't use 0. Okay, now for the fun part. We're going to do some operations on functions. Here in this chart, we're going to let f and g be any two functions. We can make a new function h defined by performing any of the 4 basic operations, which are addition, subtraction, multiplication, and division, on the functions f and g. So this is kind of the not too hard part if you think about it. The addition operation is saying, okay, we're going to make this new function h based on just adding f of x and g of x. So the example they give us, they want f of x to be 2x and g of x to be the function x plus 1. So h of x would just be 2x plus x plus 1. Guys, all you have to do is add like terms and you'd end up with 3x plus 1. That would be your h of x function. You could do subtraction. If the function h of x was f of x minus g of x, well, now all we'd have to do is distribute the negative and add like terms. And 2x minus 1x would be x. And if you multiplied the negative to the 1, you'd get minus 1. So h of x here would be the function x minus 1. You could also multiply functions together to make a new one. If you multiplied f of x and g of x, you'd have to distribute 2x times x and 2x times 1. Creating 2x squared plus 2x. And then finally, division. If I were to do f of x over g of x, I'd get 2x divided by x plus 1. Now notice, they don't have any common factors. You cannot cancel the x's, and just to show you, remember, factors means the things that are being multiplied. The only things being multiplied in the numerator are 2 and an x. In the bottom, I'm not multiplying x and 1, I'm adding them. So x plus 1 is the factor of the denominator, and there's nothing to cancel. So that's actually just simplified. Now, when we talk about the domain for adding, subtracting, multiplying, or dividing two functions, there's 3 steps that you have to take. First, you're going to find the domain of f of x, then find the domain of g of x, and the third and final step is to pick the domain that works for both, or the most restrictive. In the case of division, f of x over g of x, you have to make sure that g of x equals 0. And if you think about it, that would make sense, because what if g of x equals 0? Wouldn't that be f of x divided by 0? And isn't that undefined? So we would have to do one more step if we have that division. I'm going to show you one last set of examples before I let you try some in a little self-quiz, and we'll be done with the video. Example 1 says, perform the operation and state the domain if f of x is 2 square root of x and g of x is x squared. For A, I have to do f of x plus g of x. Okay, well f of x is 2 square root x plus g of x is x squared. Now we talked a little bit last section about like terms, and I hope you realize that there's no way in the world we can add 2 square root of x to x squared because they are not like terms.
To pick up where we had left off, f of x plus g of x for part A would be 2 square root of x plus x squared. Now we discussed in the last section, when you add terms, they must be like terms, and clearly the square root of x right here is not a like term with x squared. So we can't possibly add these two terms together, and there's nothing that we can do to simplify that square root of x. There's no perfect square in the radicand. So we're stuck right here, and that is what f of x plus g of x is. It's just 2 root x plus x squared. Now when we do the domain, there are a few steps that we need to take. Remember, first step is to find the domain of f of x. The domain, and instead of writing out domain all the time, I'm just going to write d, if that's okay with you guys. The domain of f of x, which is just 2 square root x, is interesting because I do have an even root, right? This is an even root. So if there's an even root there, I have to make sure that the radicand x is bigger than or equal to 0. Now, so we've done step 1. The domain of f of x is all x values bigger than or equal to 0 because of that even root. Now, g of x is what we have to find for the second step. So we're going to find the domain of x squared. Now, a lot of students, they'll say, oh, we have an even root because I see a 2 there, and that's an even number. Guys, when you square something, you're not taking a root. I can plug in any number I want and square it, whether it's positive, negative, it doesn't matter. You tell me a number, I'll square it. It's not a problem. This is not a domain issue. So the domain of x squared is all reals. Now, the third step is to use the most restrictive domain, meaning I'm going to need to put the fact that I have to have x values bigger than or equal to 0 together. Along with that, I can use all reals. Well, the most restrictive domain is all x values bigger than or equal to 0. I cannot use all reals, obviously, if I have to also make sure I don't use x values bigger than or equal to 0. So putting it all together, the final answer for my domain for f of x plus g of x is going to be all x values bigger than or equal to 0. Let's take a look at part B. F of x minus g of x. F of x would be 2 root x minus g of x, which is just x squared. There is nothing I can do there. I cannot subtract those because they're not like terms, so we're actually done just writing that. Now, if I were going to find a domain, I'd have to follow the same steps. Step 1, wouldn't that be exactly the same as what we did for the previous example for f of x plus g of x? I'd have to find the domain of f of x, and I would still get all x values bigger than or equal to 0 because f of x is the same function. It's still 2 root x. Step 2, I'd have to find the domain of g of x, which is still the same as step 2 in the previous example. So I'd still end up with all x, or all real numbers, all reals, and my step 3 would still be the most restrictive of both of the previous domains, and that would be all x values bigger than or equal to 0. So this would be the domain of part B. Let me kind of separate this out. Part C, we actually get a little bit of work to do here. For part C, I have to do 2 root x times x squared. Now, at first glance, it may not look like you can do anything here, but if you think about it, the square root of x is the same as x to the 1/2 power, right? And if we're multiplying that to x squared, hopefully you recognize we can use the product of powers property, and I can add these exponents of 1/2 and 2. So if you add 1/2 and 2, that'd be what, 2.5, which is the same as 5 cut in half. So if you got a common denominator and added them, you'd end up with x to the 5/2 power. And this would be the function f of x times g of x. If we go through the same steps, step 1, finding the domain, would still be find the domain of f of x, which was 2 root x. And remember, we already did that. We know the domain for that is all x values bigger than or equal to 0. Step 2 would still be to find the domain of g of x, which is x squared, and we know that's all reals. And once again, for step 3, we would use the most restrictive from both steps 1 and 2, which is all x values bigger than or equal to 0. That is going to be the same. Now, the last example I'm going to show you guys before you try is f of x over g of x. And if I have f of x 2 root x over g of x, x squared, this is what we'd have. Now, I would actually accept this as my final answer, even though you might say, well, can't we subtract exponents if I write that as 2x to the half over x squared? And yeah, that is true. You could subtract exponents, but if you think about it, if you subtracted exponents, I think you'd get x to the negative 3/2, which means you'd have to throw that down into the denominator and get 2 over x to the 3/2 power. And technically we have a radical on the bottom because of that root. So if you did that, I guess I wouldn't be super picky on it, but I would leave this as is because right now there is no radical in the denominator and it's simplified. So I would accept the original just quotient, 2 root x over x squared, for your final answer. If you did happen to simplify and use the properties of exponents properly, I don't think I would penalize you for that in this particular instance. Now, as far as domain goes, we still follow all of the same steps we did for the previous 3 examples. So meaning step 1, we'd still have a domain of f of x of the 2 root x, right? And we'd have all x values bigger than or equal to 0. Step 2 would still be to find the domain of the x squared function, which would be all reals. Now, but step 3 would still be using the most restrictive, all x values bigger than or equal to 0. However, if you take a look at the top, in the case of f of x over g of x, we have to make sure, in addition, that g of x cannot be equal to 0 because we have a fraction and we have x values in the denominator. So I also have to be sure that x squared, rewrite that so it's not so large, I also have to make sure that x squared should never be equal to 0, and that means that x cannot be 0. Because if x is 0, doesn't that denominator x squared become 0, and I'm dividing by 0, which is undefined, so I cannot plug in 0 anymore, along with the fact that I got to use x values bigger than or equal to 0. If you think about putting this fact together, that x shouldn't be 0, and you want to use all x values bigger than or equal to 0, we get a final domain of x values that are strictly greater than 0, meaning I don't want to use 0 because that would give me a 0 in the denominator, and I wouldn't want to use negatives because that would be violating the even root. This is my final domain. Okay, what I want you guys to try now is your self-quiz. You have similar problems to try. I would like you to make sure that you do the operation and state the domain, and we'll talk about it in class later. Thanks for watching.